This presentation is going to be on achieving higher reliability and sustainability with plastic pressure piping materials in mechanical applications. And this presentation is sponsored by the Radiant Professionals Alliance, the RPA, I should say that first off. So thank you to the RPA for sponsoring and hosting this and organizing it and promoting it and getting you all here. So I really appreciate that. So my name is Lance MacNevin. I am the Director of Engineering for the Plastic Pipe Institute's Building and Construction Division. So that's my day job. That's actually the job title. And what that means is that I'm a staff engineer with the Plastics Pipe Institute. And one of the things we work on, or some of the things we work on, is we do a lot of research with regards to plastic pipes. We do codes and standards development. We do a lot of our own publications, which I'll show some of those near the end of the presentation. We organize industry events, and of course we do education like this. I am a pipe geek. Officially, I'm a pipe nerd, I think is the backside of my business card. I actually joined the plastic piping industry in early 1993, so next week it'll be 30 years in this business, and it goes by really fast. It's a great industry. Plastic pipes are always evolving, always getting better, but at the same time, they are highly sustainable solutions for our built environment. So that's something that got me hooked way back in the early 90s, is that these pipes are better for the environment. So we just need to use more of them and replace more metal pipes with plastic. That's always kind of been my goal and my drive for all kinds of different reasons. And as an official pipe geek or pipe nerd, I get involved with all kinds of different technical committees. So of course we have probably 8,000 ASHRAE technical committee meetings here going on this week. I've made 3 of them. But I also get involved with, here's the alphabet soup, ASTM, that's the American Society for Testing and Materials, that writes standards for thousands of products, the American Society of Plumbing Engineers, American Waterworks Association, the Canadian Institute of Plumbing and Heating, Canadian Standards Association, Hydronic Industry Alliance Commercial, International Association of Plumbing and Mechanical Officials, International Code Council, the International Ground Source Heat Pump Association, NSF is NSF, and RPA is the Radiant Professionals Alliance. So that's your acronym dictionary, and I'll try to not use many more. So the organization I work for, the Plastics Pipe Institute, we call that PPI, so there's another acronym. PPI, it's a nonprofit trade association that first formed in the early days of the plastic pipe industry in 1950 in the United States. So yes, people were making plastic pipes back in 1950, even before that, believe it or not. But a bunch of engineers got together in 1950 and said, we need to standardize how we make these pipes and how we test them and dimensions and things like that. So those early engineers ended up forming the group that became the Plastics Pipe Institute, now 73 years later. So it's a nonprofit trade association based down in Irving, Texas, but we serve our members all across North America, and we are supported by member dues. We have over 170 firms that are firms involved with the piping industry that are members of our organization. They pay dues each year to belong and to support the work that we do on behalf of the industry. So that's how the PPI exists. Our mission, as you can see here, to advance the acceptance and use of plastic pipe systems through research, education, technical expertise, and advocacy. So there's only 12 employees at PPI, but with 170 member companies, when we all get together, it's about 300 people that get together in a big meeting to talk about pipe testing and research and things like this over a couple of days, a couple of times a year. So it's a pretty big organization. And it's a nonprofit. We don't have anything to sell, so I'm not here to sell anything. Our job is just to share information and knowledge through education. Within PPI, if you're trying to find information about the pipes we're going to talk about here today, we have 5 divisions because there's different kinds of pipes for different applications. So all the pipes related to plumbing and mechanical systems are covered by the Building and Construction Division, or BCD, another acronym. And the Building and Construction Division focuses on plastic pressure pipes used for this list of applications here. So those are the things we're going to talk about today. And then the materials that we represent are essentially the high temperature plastic pipe materials. So CPVC, high density polyethylene, we talk about that for geothermal systems within this group at PPI. And then of course PEX, PERT, PEX aluminum PEX, and different types of polypropylene pipe. So those are the kinds of materials we're going to be talking about here today. Now, to understand really what is this course set out to do, here's a bit of a course introduction. And I'm actually going to read this so I get it right. So the introduction is that specifiers and designers of mechanical systems have several options when selecting optimal pipe and fitting materials for each application. Considerations include, so when you're trying to decide what type of pipe should we use, That includes temperature and pressure capabilities, of course, material durability, convenience of handling, joining procedures, cost, and long-term reliability. Kind of obvious, but all of those things are part of the piping selection decision. And then some other practical selection factors include sound, vibration, and heat transfer. Those are all the things a pipe has to do, right? Pipes are actually really exciting when you think about it, because their job is to keep the water inside, stay behind the wall, stay inside the floor, don't ever let the water out, and then just last there for a really, really, really long time. So if you get everything right, that's how a pipe does a good job. So you might think of them as not exciting, and they're not supposed to be exciting to the user, but to the people that build them and design them and specify them, they're kind of exciting because you have to get all these things right. And then there's also the aspect of sustainability and embodied carbon and the environmental impacts for producing various types of piping materials. So all of those things are kind of considerations when choosing the right type of pipe. So that's what this course is going to be talking about. We're going to demonstrate that plastic pressure pipe and fitting materials deliver reliable and sustainable solutions for many mechanical piping purposes, and will help the audience, that's you, to select which piping material or materials are best for the different applications. And this is the main list of the applications we're going to be talking about here. Hot and cold water plumbing, hydronic heating and cooling, snow and ice melting systems for outdoor surfaces, not so necessary in Atlanta, but much of the country really needs those. Geothermal piping systems, indoor and outdoor part, and then district heating and cooling. So we'll be touching on all of those things. So this is the official course outline. We've got essentially 4 learning objectives here, 4 main points we're going to be touching on. First, we're actually going to talk about the 5 plastic pipe materials that are really good options for different types of mechanical applications. And they're not all the same. There's different types of plastic, of course, just like there's different types of metal. And some of these are flexible, some of them are stiff. Some of them have great high temperature capability, some of them not so much at the high temperature, better at the low temperature. So they're not all interchangeable. There's different pipes for different purposes. So that'll be the first thing we'll talk about. And then we'll give examples of where you use these different materials in different applications, like I showed, different applications. And we're actually going to talk about the top 10 applications for plastic pipe and give examples of each one of those in learning objective number 2. And number 3, we're going to discuss the design of piping systems in terms of sizing the pipes for flow and pressure loss, how to deal with thermal expansion and contraction, and then how to kind of calculate the static water column that can result from elevation in a vertical piping column. And there's an online calculator that you can get for free that'll actually help with all those different design considerations. So we'll show you how to use that. And then the 4th part is to explain how to use some industry resources, again, to help with pipe selection. So it's a lot to go over. And we're going to start with the advantages of plastic piping systems. There's a lot of words on this slide. I apologize. I don't want to read them all. But you can get an idea that the list is actually pretty good for the advantages of plastic piping. The first 2 have to do with plumbing. So if we're dealing with hot and cold water, you need to make sure that the piping and fitting materials are obviously safe. And that is ensured through testing and certification to the standard known as NSF ANSI CAN 61 is the number for that standard. And it's called Drinking Water System Components Health Effects. So that's the testing that's done to make sure that these materials are safe to transport or potable water. And then, of course, the piping materials have to be resistant to disinfectants in the water, like chlorine and chloramines. And there's official test methods to prove that they are. One of the good things with plastic pipe is there's no flame used in joining. I mean, how often do you see in the news that some big apartment building just went up in flames during construction because of, a plumber's torch? Unfortunately, set something on fire, and it was a windy day, and they couldn't put it out. With these plastic piping materials, we're not using flame to join them, so that's kind of an inherent advantage right there, the reduction of fire. Lower thermal conductivity. Plastic is less thermally conductive than is metal pipe. And for most of the jobs we use plastic pipe for, we want the heat to stay in or the heat to stay out if it's a cold water pipe. So that's an inherent advantage. Plastic pipes are going to be resistant to corrosion and tuberculation and mineral buildup. That's kind of inherent. They're clean to work with and easy to work with for people on the job site. They're lightweight, which makes it easier to transport the pipes on trucks, but also easier for the workers on the job site. So you have potentially less chance of worker injury on the job site when they're carrying around plastic pipes that weigh 1/4 of the amount of metal pipes for the same diameter. That's a big advantage. They've got durability and toughness to withstand tough job site conditions. They can install faster. In days of worker shortages and, everybody is saying, I can't get enough workers. If you have a material that installs faster and saves maybe 20% of the installation time, that's a big advantage right there. And then there's practically no scrap value for the plastic pipes, so nobody's really breaking into job sites to steal plastic pipe because you're not going to be able to sell that at the scrap dealer, unlike some metallic pipes. So we're going to introduce plastic pipes by saying that these are better materials, which give you longer life, better value for the job, and 99 times out of 100, they're also going to be less expensive than metallic pipes as well. So a lot of inherent advantages here. And then to touch on the sustainability side, I have a few graphs that come from a European association known as TEPFA. And this group in Europe has actually commissioned several different life cycle analysis, or LCA studies, comparing the common types of plastic pipes with metallic pipes that would be used for the same purpose. So in this graph here, and they evaluate these pipes in 7 different criteria. And you probably can't read all the details down there, but all of these slides are going to be available after the presentation. And you can get all this information on the TEPFA website. That's TEPPFA, if you wanted to look it up. But in this evaluation of PEX versus copper, we see the environmental footprint, the amount of embodied carbon, the amount of energy required to make the material, far less than to make copper. Blue is the plastic and the gray is the copper, kind of normalized to the higher copper value, and this is how the PEX compares in all those different categories versus copper. So there's a far lower environmental cost to develop and produce and install PEX plumbing systems than there are for copper plumbing systems. And I don't want to kind of rush over this too fast. We don't have a ton of time to spend on all the details of this, but it's kind of inherent, and it's a big difference. It's not just that plastic is a little bit better than copper. It's a lot better than copper when it comes to the whole environmental footprint of plastic versus metal in this case. The next comparison is actually polypropylene, a type called PPR versus copper, the same kind of analysis versus the same kind of copper for hot and cold water plumbing systems. And the results are a little bit different because polypropylene is a different material than PEX is, but in every case still, the environmental costs are lower for polypropylene than they are for copper. And then the third comparison we have here is high-density polyethylene, which you don't use for hot and cold plumbing inside a building, but high-density polyethylene is used for a lot of cold water piping outdoors or indoors, and that's compared with ductile iron in this case. So that would be like water main piping materials, underground water mains. Ductile iron is often used for that, but so is polyethylene. And as well, polyethylene is winning in every single category versus ductile iron for all the different scores involved in an LCA. So all this data is available online. If you want to get into those details, we could do that afterwards, and I'm happy to provide the links and the data for those comparisons. So that's the background. Hopefully we've established now that the plastic pipe materials are sustainable, better than the metallic alternatives, and then now we're getting into the specifics of these materials. So here are the 5 different piping materials that we're going to be talking about here in alphabetical order, starting with CPVC, HDPE, PEX, PERT, and PP, which is the acronym for polypropylene. And those are the full names of the materials shown on the slide. And that's kind of a family picture. Those are all these different pipes kind of lined up for a family picture. We had them all smile and stay still at the same time so we could get one picture with all of them together. So we'll start with CPVC. And the question often comes up, well, isn't PVC just the same as CPVC? Aren't they the same material? And they're really not. So everybody's very familiar with PVC, I'm sure. It's a very ubiquitous plastic used in all kinds of things. And in buildings, PVC is used for the drain waste vent pipes in many applications. It's a low temperature product. PVC is not suitable for high temperature applications. But the manufacturers that make CPVC, they start with PVC and then they add an extra chlorine molecule to the molecule of PVC. So it's chlorinated PVC is what it is. And that extra chlorine molecule gives the product a lot of advantages, including capability of withstanding really high temperatures and very high chemical resistance for a lot of chemicals that are used in process piping and things like that. So there really is a big difference between CPVC and PVC. There's a big difference in price as well. The CPVC is way more expensive, but it should be because it's a different material and has a lot of extra capabilities. So that's kind of just the first thing to clarify. And CPVC is approved in all the model codes for plumbing and mechanical applications, so we'll show that a little later. So CPVC, it's a high temperature plastic. It's always pressure rated for use up to 200 degrees Fahrenheit, and in some cases even more than that if you would need it for some sort of industrial application. We don't have temperatures that high in plumbing and mechanical, obviously. And it's been around for a long time. In fact, CPVC was first used for a plumbing system in 1959 in Ohio, I think. So it's been around for more than 60 years now as a plumbing material, and then for many decades as a fire protection material and a mechanical piping material for hydronics as well. CPVC materials, they're rigid, straight lengths. They're used with molded fittings, as you can see in the pictures there, and they're available in both copper tube size dimensions, like copper tubing, or iron pipe size dimensions. So you can get CPVC tubing or CPVC pipe. Those words just refer to the dimensions of the outside diameter. And then they're produced in accordance with standards. We love standards in the pipe business. And there's 3 different ASTM standards for different types of CPVC, depending on whether it's CTS or IPS, depending on whether it's an SDR wall type or Schedule 40, Schedule 80. And then there's also a CSA standard for CPVC pipe and tubing as well, shown there. The configurations, like I said, it's available in straight lengths. This is not coming in coils. The tubing dimensions are available from 1/2 inch up to 2 inch, nominal tubing size. And then the iron pipe size, you can get those up to 24 inch or possibly even larger if you need, thousands of gallons a minute for hydronic heating or something like that. You could get very large CPVC pipes to handle that. And then the fittings are molded. So how is it joined together? There's really 4 different ways of joining a CPVC piping system. Solvent cement is by far the most common type, and I'll explain how that works in a second. You can also get push-fit fittings that work with the CTS, the copper tube size version, where you just push them on. And the example up here is a fitting where you can actually join PEX and copper and CPVC all in the same fitting because they all have the same outside diameter. You can actually use grooved mechanical fittings like those from the Victala company. And then you can also get flanged fittings. So if you're bolting CPVC pipe up to a flanged valve, you can get those kinds of adapters like in the right-hand picture. But by far the most common version of joining CPVC is using solvent cement. And the thing we need to clarify here is that solvent cement is not glue. A lot of people think of it as glue. Glue is a substance that holds 2 things together, like gluing the sole onto the bottom of your shoe. That's glue that holds the rubber sole to the bottom of your leather shoe. The similar materials, and the glue sticks to both and holds them together. But solvent cement is not that. Solvent cement, it's a solvent which has CPVC in it, which when you apply the solvent to the outside of the pipe and the inside of the fitting, and then you push the 2 of them together, the solvent basically dissolves a little bit of the pipe surface and a little bit of the fitting surface and allows the molecules of one to flow into the molecules of each other. And then when that solvent evaporates and dries off in an hour or 2, essentially you have a continuous monolithic joint in between the 2. So there's no layer of glue in between the pipe and the fitting holding them together. Basically, the pipe and the fitting have been welded to each other. You didn't need heat to do it, you just needed the solvent to do it. So it's essentially a welded joint. So when you do solvent cement, that's what you end up getting. It's a complete monolithic welded joint. So it really is a reliable welding technique. One thing to be aware of with CPVC, though, it's very resistant to some chemicals. Other chemicals, it's very sensitive to. So when you are using CPVC on a job site, you have to be very careful about what chemicals might be touching the outside of the pipe especially. Different types of fire-stopping materials or caulking and things like that may actually cause problems with the pipe over time. So the way to find out is, a lot of research has already been done in this field. You have to check with the manufacturer. And the biggest manufacturer of CPVC material in North America, it's a company called Lubrizol out of Ohio. And they've tested hundreds and hundreds of different job site materials with their CPVC pipes and fittings. So if you go to their website and you search for FBC system compatible, and there's even an app for that, you can download it. You can basically look for a type of drywall mud or caulking or wiring insulation or something like that and find out, is this going to be compatible with touching that pipe or not? So we do recommend that people go get that information and check that when using CPVC for anything. So to wrap it up for CPVC, it's a strong, rigid piping material, high temperature capability, and available in a wide range of sizes, a wide range of wall thicknesses, depending on the pressure rating that you need. It's going to be really economical, more economical than copper or steel, and there's several domestic sources for it. So that is CPVC. The next pipe we're going to, yes, question?
Is there any regulations about CPVC piping in the future for plumbing?
Not that I can think of. I mean, it's been approved for plumbing for decades and decades, so what are you thinking of?
Well, someone had told me that there might be some regulations about PVC piping because of the chlorine system and whatever. So I was just wondering if you know of anything that might be.
Not definitive, slightly maybe. I've heard of some of that tough stuff being talked about in Canada. But if you could talk to me about it afterwards, I can tell you what kind of the crystal ball might hold in the future for that. But I don't want to get into it now because it's chemical terms that I'm not even going to say right the first time, and it's better if we just discuss it privately. Yep.
And you might be getting to this at some point, but can you speak to the compliance with like plumbing rated pipe for CPVC or other materials?
Hold that thought, please. I do have slides on that. Yep, I'm glad you brought it up. Because then that makes it look like I was kind of reading into the future and I knew exactly what you were going to ask, because I have a slide on that, so thank you. I'll pay you later. The next material to talk about then is high-density polyethylene, or HDPE. One of the most popular plastics in the world. I mean, your gas can, if you get a 5-gallon, jerry can for gasoline, it's probably made of HDPE. Your detergent bottles, most of the nasty chemicals you buy at the store for killing weeds, whatever, those are in HDPE bottles. There's different types of HDPE for different applications, and a lot of HDPE is also used in piping. Most of it is used for piping for water mains and also geothermal piping systems. Those are almost exclusively HDPE. But there is also some applications inside the building for HDPE as well. In some cases. So that's what we're going to be talking about here in a few minutes. HDPE is not a high temperature material. In fact, it really maximum exposure temperature for HDPE in a pressure system is 140 degrees F. Most of the applications for HDPE are room temperature water, or maybe up to 100 degrees Fahrenheit, but generally not beyond that. It has very good chemical resistance. Like I said, most of the chemicals come in HDPE bottles, so it's inherently good there. And like I said, we love standards, and there's a bunch of different ASTM standards and a CSA standard for PE pipe as well. In terms of how PE pipe is joined, and I'm not going to get into a lot of the nitty-gritty about each of these pipe materials because that would be a 4-hour course, so I'm really kind of giving the highlights. So if you want more information, I'll show you how to get that when I'm done. For a PE pipe, the way it's joined, there's typically 3 different types of fusion, which is done with PE pipe. And it's not solvent cement fusion or solvent cement welding. It's actually heat fusion that's done to join polyethylene pipes to pipes and pipes to fittings. The first one that's shown here in the list is called butt fusion, and that's this picture here where you have one piece of pipe heated and another piece of pipe heated, and then they're pressed together with a machine, so one is butted up against the other. And if you get them to the right temperature and with the right force and hold them together for a little while, the molecules from one surface will flow into the molecules from the other surface, and again, makes a monolithic pipe structure. So there's no solvent cement or glue or anything holding it together. When the fusion is done, it's like a continuous piece of pipe. Extremely reliable. For smaller diameters, we often use molded fittings to join PE pipe. In this picture, it's just some caps on the outside of PE pipes. Those are like geothermal test caps holding the pressure in. And in that case, what we do is we heat the inside of the fitting and the outside of the pipe and then squeeze them together with pressure, and the fusion takes place once they're joined with each other. And then there's also the process of electrofusion, which some people really prefer this because it's easier to deal with on the job site in most cases. With electrofusion fittings, it's a polyethylene fitting with copper wires embedded in it all the way around. And with these little stubs or electrodes sticking up, you connect that to a computerized machine, which actually applies a certain amount of electrical current, enough to heat up the copper wires, which heats up the fitting, which essentially also heats up the outside of the pipe, and then the pipe and the fitting fuse to each other. It's very computer controlled. The user operator doesn't have to do a lot. Once you join the things together, plug it in, turn on the machine, and when the beeper goes, that tells you it's done. So it's a very straightforward process. So that's just kind of a bit of an introduction into HDPE. Again, tough, durable, flexible pipe. HDPE is normally coming in coils if you want it, or straight lengths if you prefer that. It's been around for more than 40 years, wide range of diameters. I mean, you can get polyethylene pipes that you can walk through for very large mechanical systems. If you need pipes that large, it's available. You can also get mechanical fittings, which I didn't show you, but Victaulic and other companies like that make a wide range of mechanical fittings. So if you're not comfortable with fusion or you don't have that equipment, you can also use mechanical fittings that bolt together with PE pipe as well. You groove the outside of the pipe in some cases, and it's available in a wide range of diameters and wall types depending on the pressure rating that you need. So that's your introduction into HDPE, and that's a very large manifold system for a geothermal system made of HDPE. So used for large systems. The next material to introduce then is PEX. And you've probably all heard of PEX because it's become by far the most common plumbing pipe material in the United States and Canada over the last 25 years. And in fact, some of the data that we have from an institute that tracks this kind of thing shows that more than 2/3 of all the houses built in the United States right now are using PEX as the hot and cold water pipe. So it's a very common material. It's actually not new. It was actually first introduced in 1972, which, if you check the math, that was actually more than 50 years ago now. So 2 different European companies both started producing PEX tubing in 1972 for sale. So it's been around for 50 years. It's not new. PEX is polyethylene that's cross-linked. So it is HDPE, but as part of the manufacturing process of making PEX, those HDPE molecules actually link with each other into really long hydrocarbon chains. So essentially, if you have a piece of PEX tubing, most of it is the same molecule, which gives it a lot of great toughness and resistance to slow crack growth and notching and cracking and things like that, and also gives it very high temperature resistance. So PEX tubing can withstand much higher temperatures than regular polyethylene, and in fact, all the PEX tubing that's out there is tested at temperatures beyond 200 degrees Fahrenheit. It's all rated for at least 180 degrees Fahrenheit continuous operation, but it's capable of temperatures far beyond that. The piping industry is very conservative. The vast majority of the PEX that you're going to find in North America, it's copper tube size, so it has the exact same outside diameter as copper of the same name. And again, we love standards, so it's produced in accordance with ASTM F876 and or CSAB 137.5, and you'll find those standards marked on any PEX tubing that you're going to buy at the store or at a wholesaler or something like that. It is recognized in all the model codes for plumbing and hydronic mechanical applications, and it's used for a lot of other applications as well, because it's a pretty universally accessible pipe. I mean, it can be used for almost anything. Great chemical resistance and everything else. In terms of how it compares with HDPE, because PEX is more expensive than HDPE. It can do more than HDPE in a lot of cases. It has greater capabilities. It's more expensive. It's harder to manufacture, so it costs more to make it, so that's why it's more expensive. But in terms of how it compares with HDPE, when we cross-link these molecules, so this is like one polyethylene molecule on the bottom and another one on the top, and then there's links joining them together, that actually spaces them out in a certain way. Like imagine a chain link fence where all the wires are at exactly the same spacing from each other. And that actually reduces the density of the PE material slightly when you convert the polyethylene material into PEX. So with lower density, it also has slightly lower stiffness. So the same wall thickness of PEX versus a wall thickness of polyethylene, the pressure rating on the PEX is going to be a little bit less. Generally, that doesn't matter in plumbing and mechanical applications. It's still more than strong enough than what you need, but that's just a question that comes up sometimes, is how does the strength of PEX compared with polyethylene? PEX is actually more flexible and can be bent tighter and pulled more and everything else as compared with polyethylene. Also makes it easier to install, especially in cold weather, if you need to be bending it. I'm not going to get into the details of material designation code, but for mechanical systems, there's something that we need to talk about really quickly, and that has to do with the concept of oxygen diffusion through a pipe wall. Because if we're going to be using plastic tubing or piping in a closed-loop hydronic system, is everybody here involved with hydronics? We know what we're talking about? Okay, a lot of hands, good. PEX tubing was first invented in the early 1970s for radiant heating systems. And in the 1970s, people used cast iron boilers and cast iron pumps. That's all they had back there in the 1970s. And when they started using thousands of feet of plastic tubing for radiant heating connected to a cast iron boiler, they started getting problems with those boilers. Those boilers would start rusting from the inside out after just a few years of operation. The only way you can get a boiler to rust in a closed-loop heating system is there needs to be some sorts of oxygen getting into the water, because rust is basically steel combined with water and oxygen. That's how you make rust. So in a closed-loop heating system, normally you don't have oxygen unless it's getting in through the pipe wall somehow or through some hole somewhere. So they learned that the hard way in Europe in the early 1970s that regular PEX tubing actually can be permeated by oxygen molecules. So an O2 molecule from our atmosphere can actually pass in through the molecular space on the PEX molecule here and be absorbed into the water inside the pipe. The oxygen doesn't hurt the pipe, but it can be absorbed into the water and basically give you oxygenated water, which can then cause corrosion of any cast iron or steel component that the water is coming in contact with. So not a good thing, obviously. It causes them to fail. So what the engineers in Europe did by the late 1970s is they figured out there's another type of plastic called ethylene vinyl alcohol, or EVOH, that could be co-extruded or applied in very thin layers to the outside of the PEX material itself, really thin layer, like 0.02 of an inch thickness is all you need, and that would make the PEX tubing oxygen tight. So if you're using PEX tubing in a closed loop hydronic system and you don't want the boiler or pumps to be rusting from the inside out, you need to make sure that you're specifying PEX tubing with an oxygen diffusion barrier, again, which is this thin layer on the outside of the PEX tubing. Now, the oxygen barrier itself doesn't stick to PEX itself, so there's a thin adhesive layer that's applied in the factory as part of the extrusion process, where you put this thin adhesive layer first over the PEX, and sometimes that's colored, sometimes it's not. I mean, it could be green, it could be orange, it could be red, and then the oxygen barrier coating itself is perfectly clear on the outside. You can't see that, but sometimes you can see the adhesive if it's colored. So that's an important thing to know if you are using PEX for closed-loop hydronic systems. Now, when it comes to joining PEX, PEX is not joined via heat fusion. Rarely you can join PEX with electrofusion, but that's rarely done. The vast majority of PEX fittings work on a principle of compression, which means we're actually putting something inside the PEX tubing and then something outside the PEX tubing and compressing the tubing around the parts that's on the inside, the insert. So this picture here is a family photo of lots of different PEX fittings that are available on the marketplace from different manufacturers. So this isn't all one system. This is about 5 different systems just kind of posing together here. And they all essentially are working though on the process of compression, where you're making some sort of pressure on the tubing. So one of the common types of PEX fitting systems that was pioneered in the early 1990s is the crimp ring fitting system. So on the left, we have an actual brass fitting with ribs on it, and that just presses inside the tubing itself, just by hand. And then this is a deformable copper ring that goes on the outside, and you can use a manual tool or an electric tool that applies pressure to the ring and essentially crimps it down and reduces the diameter of the ring, and that compresses the tubing around 1 or 2 of the ribs on the inside. And it actually creates a really tight seal. These fittings are actually tested, all the PEX fittings are tested according to various standards, and they have to show essentially that they are stronger than the tubing itself. So if you do a burst system test of a bunch of tubing with fittings inside and you blow it up, the tubing is going to break. A hole through the wall of the tubing will rip, but the fittings themselves won't leak. If they did, then they're not approved for sale. That wouldn't be an eligible fitting system. So the fittings are always stronger than the tubing itself. So this is a very common fitting system right here, and this is made to its own ASTM standard called F1807. That's a standard that controls the dimensions and the material properties for the insert fitting and the copper crimp ring. So that's one fitting. Another common popular fitting system is known as a cold expansion fitting with a PEX reinforcing ring. And the principle of this one is we want a larger diameter fitting going inside the PEX tubing, so we actually have more volume and less pressure loss inside the fitting. So to get that bigger fitting inside the PEX tubing, first you expand the diameter of the PEX tubing with a segmented expander that goes inside the tubing and increases the diameter so you can put an oversized fitting inside of it. The fitting also has sealing ribs on the outside of it. And PEX is like an elastic material, which means if you stretch it, it'll spring back. Or if you stretch it this way and change its diameter, it'll go back to its original diameter over time. But to make this fitting system even stronger, it uses an extra ring of PEX on the outside of the PEX tubing itself. So you slide that ring over the PEX tubing and you expand both together, usually with an electric tool, electrohydraulic tool. That's a big one in that picture. And you expand both of them together, and then you push the fitting inside, and then pretty quickly, the PEX tubing with the ring on the outside are returning back to the original diameter and creating a tight compression seal on the outside of that fitting and the inside of the PEX tubing. So that's a very reliable fitting system that's been around for at least 30 years, possibly more. And that fitting in North America is produced and tested according to ASTM F1960. So there's multiple manufacturers that sell these fittings, and all of those fittings are produced according to ASTM F1960. There's a press fitting that's on the market, and this is similar to the copper crimp ring fitting, except different, which means it works in the same principle as the copper crimp ring fitting. There's a metal or insert that goes inside the tubing, but instead of a copper ring on the outside, it's a stainless steel press sleeve on the outside that's pressed down with either manual or hydraulic electric tool. So that's what this tool is doing here, pressing down on that stainless steel press sleeve, which compresses the tubing on the insert fitting on the inside. And whether that's made of metallic fitting material or plastic fitting material, there's different ASTM standards that apply to that kind of a fitting system. And then there's another version of a cold expansion fitting system that actually uses a ring of PEX on the outside that isn't expanded first. In this PEX fitting system, you expand the tubing, and here's a PEX ring over here, and you put the fitting inside, and then there's a tool that's used to slide that PEX sleeve over the end of the tubing, and it creates the same type of a compression seal. And those are kind of like the most common PEX fitting systems in North America. There's even others. But all of those fitting systems are tested to certain standards and certifications and things like that. I'm not going to get into all the details of the testing that's done, but trust me, they're highly reliable fittings that are stronger than the tubing itself. So hopefully that gives you a good introduction into PEX. I have two more materials to go, and then some other information to share as well, so I'm not going to slow down yet. The fourth material we're going to introduce is called PERT, which stands for polyethylene of raised temperature resistance. This is also kind of like a supercharged version of polyethylene pipe. It is HDPE, but it's a version that's manufactured and compounded to have higher temperature capabilities. Remember, regular polyethylene pipe, maximum exposure temperature 140 degrees. PERT, it's tested and designed and certified for continuous operation of 180 degrees. It's produced in the exact same dimensions as PEX, so it's kind of a substitute for PEX, but it's not a cross-linked material. So if you think of the pricing of these things, there's PE, and then there's PERT, and then there's PEX at the top, because PEX is cross-linked. But PERT kind of fits in that territory between PEX and regular polyethylene, and it's almost like a hybrid version between the two of them. It's produced to PEX dimensions. It works with all the PEX fitting systems that are on the market, but it's also a polyethylene pipe that can also be joined via heat fusion too. So if you wanted to build a PERT piping system using polyethylene fusion fittings, you can also do that too. So it's really kind of a neat material in that sense. And there's different ASTM standards for PERT systems and a CSA standard. So ASTM F2769 is the standard for PERT tubing for potable water, and CSA B137.18 is the CSA standard for PERT tubing. And like the other materials that we showed, this is approved in all model plumbing and mechanical codes. And you can also get PERT in large diameter piping dimensions. So if you needed to use like a 2-foot diameter pipe to move a lot of heated water around on a university campus, underground piping and a district heating system or something like that, and this water temperature is going to be running at temperatures up to 180 degrees, you can actually get PERT available in large pipe diameters, and that can be joined again with mechanical fittings like Victaulic type fittings joining PERT, or you could also do heat fusion for the very large diameter PERT as well. So it's kind of a neat material in the sense that you can get it in small tubing dimensions or really large pipe dimensions as well. And then the fifth material we're introducing, and the last of the different materials, is called polypropylene. And there's two subtypes of polypropylene pressure pipe material, and those are known as PPR and PPRCT. I'll explain what that means in a second. But polypropylene is also a high temperature piping material. It comes in straight lengths. It's rigid. It's not on little coils or something like that. But this was first developed and introduced into Europe in the early 1980s, which, again, we have to do some math, but that's about 40 years ago. So polypropylene has been around in Europe for about 40 years and about 20 years in North America. And if you go down to the trade show floor, I think you're going to find 5 or 6 companies with polypropylene pipe available for sale. So it's widely available in North America now. The polypropylene pipe that we have in North America, it's made to an ASTM standard and a CSA standard, but the dimensions of it are also the exact same dimensions as what's used in the rest of the world. So the exact same pipes they use in Germany or the UK, which could be like a millimeter pipe, 50 millimeter, 75 millimeter, 100 millimeter, those are the exact same pipes and fittings we use in North America. And the truth is, the water in the pipe really doesn't care if it's a metric pipe or an inch-sized pipe. All the water really cares about is what is that inside diameter of the pipe. So don't be concerned with that. We can help design and size the systems very well. Different manufacturers of polypropylene use different colors. So some make it green, some make it blue, some make it gray. So these could all be the same material, but colored in different ways. Manufacturers can have kind of their own customized color scheme. So the PPR version, the full definition of it is shown there. It stands for random copolymerized polypropylene. And then the PPRCT version is kind of the next generation of PPR, which stands for polypropylene random copolymer with modified crystallinity and temperature resistance. It also has higher strength. So a PPRCT pipe has about a 25% higher tensile strength and a 25% higher pressure resistance, pressure capability for the same wall thickness as a PPR pipe. So it's basically two different grades of the material. In terms of joining polypropylene, it's also done via heat fusion, so very similar to the high-density polyethylene joining procedure. You can have socket fusion, butt fusion, or electrofusion. For small diameters, they're normally using socket fusion fittings, but when you get to larger diameters, you're normally using butt fusion at that point, just pipe to pipe. There's a small diameter fitting being installed with a pipe there with an electric heating iron that heats the outside diameter pipe, and another one heats the inside diameter of the fitting. And then over here, it's a very large commercial job at an Air Force base where these big prefabricated sections are made on the ground, and then the building is built around them, in this case, I think. And then for electrofusion, I mentioned that earlier, electrofusion is a joining type for polyethylene. You can also get electrofusion fittings made of the polypropylene material, the PPRCT. And again, those fittings have the copper electrodes built into the fitting itself with copper wires embedded in the fitting. So when you prepare the pipe end, put it inside the fitting and connect it to the right machine, it'll send a current through these copper electrodes, which heats the inside of the fitting and the outside of the pipe and fuses the two of them together. So it's very clean process, very easy for the installer on the job site. There we see a nice mechanical room there, all done with PPRCT and electrofusion fittings in that case. So that's your introduction to the fifth of the piping materials. Again, that's kind of the summary of the information on polypropylene. Now, I've only got 20 minutes left, but I still have a lot more to show. So to get into the code compliance of all these piping materials, I've got a few extracts or excerpts from our biggest mechanical codes across North America. So the first one I'm going to show is the International Mechanical Code 2021 edition. And if you go to table 1202.4, that is the table in that code for hydronic piping. You can see the materials that are approved for hydronic piping, otherwise mechanical piping, in that code. So at the top, if you can read this, that's CPVC up there. And then the next one is cross-linked polyethylene. The next one is polypropylene. And the next one is raised temperature resistance polyethylene. So all four of those materials are approved in the IMC for hydronic piping. There's a separate code for plumbing, of course, so I'm not getting into that one in this presentation. In the Uniform Mechanical Code from IAPMO, all five of these materials are approved in there. And forgive me for words going over the table. The part at the top of the table is not so important. Here's the five piping materials we were talking about, all approved for hydronic piping systems in the Uniform Mechanical Code. The other IAPMO code is called the Uniform Solar Hydronic and Geothermal Code, the USHGC. And again, all five of these piping materials are approved in the USHGC code for hydronic piping applications. So full code compliance there. And in Canada, we have CSA B214, which is the installation code for hydronic heating systems, which is what a lot of these mechanical systems are. And in the CSA B214 standard from Canada, Chapter 9 is about non-metallic piping, if you can read that at the bottom, and it lists the type of approved piping materials. So the first one listed on that list is cross-linked polyethylene at the bottom there. And then on the next page, at the top, it's CPVC, and then polypropylene, and then polyethylene of raised temperature, going down the list like that. So all of these materials are approved in the major model codes across North America. Now, to address the question of flame and smoke spread rating, thank you for being patient. Here is a slide on that finally. If you are installing any of these plastic piping materials inside a return air plenum, so in a building like this, above the drop ceiling, that's probably the return air plenum, meaning we don't have a separate duct for a return air. All our return air is just in that big open space, going back to the HVAC equipment. If you put any material up there that's combustible, could possibly burn, then the material up there, according to the codes, has to be tested for flame and smoke spread. And there's a few different ways of doing this test. The most common way is a test method known as ASTM E84. There's also a couple of UL test methods used for doing that kind of test as well. And when they do that testing, what they test to see is, when we set this pipe on fire, how quickly does it burn and how much smoke does it give off? So in the laboratory, they officially set the pipe on fire with a natural gas flame, and then they measure how quickly does the flame propagate and how much smoke is given off. And that's also sometimes known as the Steiner tunnel test, and that's an actual picture of the Steiner test tunnel at UL Laboratories in Illinois. So they put the pipes inside this tunnel, set it on fire at one end, and measure the properties from there. So for most of these plastic pipe materials, they do burn. They burn very slowly, but they do give off some smoke when they burn. So each piping manufacturer has to go through this test and meet the code requirements with a flame spread number of 25 or less and a smoke developed number of 50 or less. For most of these plastic pipe materials, the way they achieve that certification is with half-inch fiberglass or another type of insulation on the outside of the pipe. Because for a lot of these plastic materials, if you apply the flame directly to them, they are going to burn very, very slowly, but they'll give off smoke. They're hydrocarbon materials, so it's almost like burning candle wax. It's often compared to a paraffin fire. If you set a candle on fire, that kind of a flame rate. So for most of these materials, they are tested and certified, but you have to use some sort of insulation on the pipes. Now, the good news is, if you're using piping for mechanical systems, you're probably insulating it anyway to keep the heat in or to keep the heat out in chilled water piping, so it's no extra cost for you to use it. You just have to make sure that the insulation that you pick for use on these pipes is the type of insulation that was tested and certified for use with the pipe so that the system is in compliance with the code. So each piping manufacturer will gather up different brands of insulation and have that testing done in the lab and then issue reports or certificates saying that our pipe meets these flame and smoke spread requirements with this insulation or this one or this one or this one. So you have to go manufacturer specific to get those exact certifications. But most of them have it on their website, easy to find. Or if not, you just call somebody and ask them, and they'll give it to you. Like these guys right up at the front here. Or Rick at the back there, or other guys in the room here today. So that's a big part of the presentation today, was on the 5 different types of piping materials that we recommend for sustainability and durability reasons and things like this. But there's 15 minutes more of the presentation, so don't go yet. And then I can stay for questions because the next one doesn't begin till the top of the hour. So the next part of the presentation, as I said, is I was going to show you the top 10 list of applications for these piping materials. So in no particular order, these piping materials can be used for hot and cold potable water, or fire protection sometimes, or water service lines sometimes, reclaimed water, hydronic heating and cooling, radiant heating and cooling, snow and ice melting, one of my favorite applications, chilled water piping, they're all approved for that, geothermal system piping, either outdoors or indoors, and district heating and cooling. Now, not every one of those pipes is approved for every one of those applications, but there's at least 2 or 3 pipes that can be used for every one of those applications. So you just have to check and get the right pipe for the right application. So for the first of them, this is where a lot of pictures come in. Hot and cold water plumbing distribution, whether it's residential or commercial, there's a pipe for that. PEX is widely used in residential, so is CPVC. When you get into commercial systems, you'll also find PEX and CPVC, and you'll also find polypropylene in commercial plumbing as well, because it's available in very large diameters. So there's some great pictures there of residential and commercial systems. And the fire protection side, one of the things that's important for getting the right fire protection pipe is, obviously you want a pipe that's not going to corrode up there sitting in the ceiling so that it works when it's needed, but it also has to go through certain testing and meet the requirements of NFPA standards. And some of these pipes do that, not all of them. CPVC, it's widely certified for both commercial and residential fire protection systems, but PEX systems, several of them are also certified for residential fire protection and some multifamily fire protection systems, depending on the PEX system. Each manufacturer has to go through that testing on their own to get that certification. But plastic can be used for that. Water service lines, bringing the fresh cold water into your building. Again, there's a plastic pipe material for that. It could be PEX, it could be polyethylene, it could be PERT. Those are the most common materials used. If you're thinking of using PEX for water service line instead of type K copper, there's actually an AWWA standard for that called AWWA C904. And in fact, a brand new version of that standard just came out on December 1st. Reclaimed water, if you are trying to collect and move reclaimed water, you can get different purple-colored coated pipes for that application, PEX and other materials. Hydronic heating and cooling systems, here's a variety of pictures showing it could be PEX or CPV, more PEX, or the one on the far right is actually polypropylene for different types of hydronic heating and cooling piping systems. Radiant heating cooling, that's where you're going to find a lot of PEX and PERT used because it's super flexible and very easy to install on the floor or a ceiling for radiant heating and cooling applications, both residentially and commercially. Outdoor snow and ice melting, again, it's going to be PEX tubing or PER tubing, very long coil lengths, continuous lengths of tubing embedded in concrete for melting the outdoor surfaces. Chilled water, all of these materials can be used for chilled water, from HDPE up to polypropylene, and they are widely used for chilled water piping systems. No corrosion, it's a good thing. Geothermal piping, polyethylene is the predominant material used in the outdoor ground loops for the pipes buried in the ground, but then for the indoor piping, all of these materials can be used for the indoor mechanical room piping and the manifolds and things like that. And then district heating and cooling. Before I came up, JAG of Ag Geothermal gave a great presentation about different types of geothermal systems, including district heating and cooling systems, sometimes known as ambient temperature loops, where you basically exchange heat throughout an entire neighborhood between schools and houses and commercial places. But there's a lot of pipes involved with district heating and cooling systems, and in a lot of cases, you can use these plastic pipe materials, which are going to be really suitable. And in some cases, you can get them in pre-insulated versions, where the insulation is already installed on the outside of the pipe in continuous long lengths to save a lot of time when installing them outdoors. So that's, like I said, my list of top 10 applications for plastic piping, for mechanical and some plumbing applications there. So again, widely used for all these different piping applications. Now, the third part here is to talk about some tools for designing the systems and sizing them correctly and dealing with thermal expansion and contraction and whatnot. And here are the kind of the top 6 questions that come up when sizing a piping system. And this applies to copper, steel, as well as plastic. These are all the things you need to know to size the pipes right and to determine the hangers and how to deal with thermal expansion, contraction, with temperature changes and things like that. So the good thing is there's an online tool for that called the PPI Plastic Pipe Design Calculator. This has been around since 2015, but it just went through some major upgrades over the last few months. It's a free online tool that you don't have to download, you don't have to register for, you don't have to give away any credit card or social security numbers or anything like that. You just go do it, use the tool, get your answer, and you can save it to your computer if you want, and then close out the session. So nobody is here to sell you anything. It's just a free online tool for the industry. So that's what it's called, and the website is simply plasticpipecalculator.com. So very easy to remember, I hope. And when you get there, you'll actually see that there's 6 blue buttons down the left-hand margin to select the different functions or the different types of calculations that can be done. The most common one is the pressure drop head loss calculation. And the way this works, just to kind of show you in pictures, is the first thing you do, if you're using this calculation, is you select your piping material. So in this example, I've selected PEX. It's a copper tube-sized PEX. I've got my wall type, which is SDR9, and I select my diameter from a drop-down menu. And there's a picture of PEX there to confirm that I've selected the right material. Then, if it's going to be a pressure drop application, you enter in how many gallons a minute you want to flow through this piece of PEX, how long the piece of PEX is going to be, whether it's 300 feet long or 22 feet long or whatever, you enter that, and then you also enter in the type of fluid, because we don't assume it's always pure water. A lot of these systems have some sort of water additive or an antifreeze in there. So in this example here, it shows it's 50% propylene glycol. That's probably a snowmelt system that would use that much glycol. And then the temperature of the fluid. Typically, you're going to size that for the coldest temperature, the worst case, because that's the one that will give you the highest pressure loss. So you enter in that data, you hit the calculate button, and then your answer will pop up in the results table. And it'll tell you whether you got turbulent flow or laminar flow, and exactly what the pressure loss is, and also what the velocity of the fluid through the pipe is, in case you're curious. And then what do I do with this information? If I want, I can hit the email button and just email the answer directly to me or somebody else. Or if I want, I can print it off as a PDF file and save that I did this calculation on this date and here is that result. And just save the PDF file on my computer if I don't want to email it to somebody right now. So those are different ways of saving it. The next function is hydraulic shock. This doesn't come up much in mechanical systems, but if it's a plumbing system and you have fast closing valves like an ACE maker valve or a washing machine, you want to know what is the peak pressure that might occur in that pipe at the highest point when there's a fast closing valve which just shuts off the flow of the water really quickly. And that really depends on the flexibility of the pipe material, and each material is going to give you a different answer here. So in this example, we've got polypropylene pipes selected, and the wall thickness and the wall type and the diameter and everything like that is shown here. And all that really matters in this case is the fluid flow rate. It's assumed this is 100% water going at that flow rate through that size pipe. And then there's a fast closing valve goes in there. And the calculator tells you, well, at that instant, when that valve closes, there's going to be an extra 42.2 psi of pressure built up in that piping, just instantaneous as soon as that valve closes. So if it was a 60 psi system, when you close that valve, now there's going to be 60 plus 42, which means there'll be 102 psi of pressure in that system just for an instant. as that pressure wave from the fast closing valve dissipates through the pipe. Plastic does a much better job than metal at absorbing surge pressures and reducing the surge pressures that come from fast closing valves, and therefore reducing water hammer and the noise that you hear, reducing pipe movement and all of that. Pipe weight and volume, if you want to find out how much actual liquid is in this piece of pipe, or if I'm doing an antifreeze system and I need to figure out how much antifreeze do I need to buy. In this example, we've got this pipe, 3,500 feet, and I want to use this mixture of antifreeze, so I enter in the data and then I hit the results, and it's telling me the dry weight of the pipe is this for that much pipe. Here is the weight full of water, and then here's how much fluids I need. So that tells me how much antifreeze to order. Thermal expansion contraction. You can do that for any of these piping materials, and it'll tell you exactly how much the pipe is going to grow in length if you increase the temperature. So in this case, it's polyethylene pipe. We're installing it at 70 degrees, but it's going to be running at 100-degree temperature with the hottest fluid inside, and the piece of pipe is 200 feet long, if you can see that. So that means over that 30 degrees of temperature change, that piece of pipe is going to grow in length by 5.8 inches over the 200-foot length of pipe. So plastic pipe, for sure, there's greater thermal expansion for plastic than there is for copper or steel. So you have to accommodate that somehow. And sometimes the way we accommodate that thermal expansion is through expansion arms or expansion loops, which look like this. That's an expansion loop, which means you have 4 elbows, so the pipe can expand back and forth this way, and the expansion is accommodated in that loop. So in this case here, let's say we're doing CPVC. It's 4-inch Schedule 80 CPVC. It's 100 foot long, and we expect a 60-degree temperature change between the coldest and the hottest operation of that pipe. And if we input that data, the calculator will tell us exactly how to design the expansion loop. So according to the drawing over here, it gives us the different lengths that we need to build a loop with 4 elbows to accommodate that expansion and contraction. Really important with piping materials that are going to expand and contract a lot. I mean, we do this with metal pipe. We also have to do it with plastic pipe. And then the final function of the calculator is the static water column pressure calculation. This is pretty simple math. You can do this on the back of an envelope, but it's something that you don't want to forget. If you're dealing with a tall building, multi-story building, and this example here, I think that's a 6-story building, that's 60 feet of elevation, and for every 10 feet of elevation height, that's 4.3 psi of water pressure for pure water at room temperature, but it could be other fluids as well or other temperatures. So in this case, you can enter in all the data about your building, select your pipe type. There's a static pressure at the top of the building. The height of it, in this case here, it's showing it's a 60-foot high building with 30% propylene glycol. So to calculate the weight of that fluid, we enter that data and we hit the calculate button, and this is telling us that the static water column pressure is going to add 41.3 psi of pressure to the pipe at the bottom of the piping network, basically in the mechanical room at the bottom. So caused by the weight of the water, that's adding 43 psi of pressure. So when you're sizing your pipes, make sure you have a pipe with a pressure rating that can withstand that. Because if you forget that, you could actually overpressurize the pipes in the bottom of the building in the lower floors. So again, free online sizing tool, just go to plasticpipecalculator.com to do all those calculations. Okay, in my last 2 minutes that are left before 3:30, I'm just going to really quickly show you some resources that we have for free on our website to help with designing these piping materials. So again, this is all from PPI. This is all free. Just go click on it and you can get it. We actually have, on the home page for the Building and Construction Division, we have a dedicated web page to each of the materials that we talked about here today, plus another material that we didn't even talk about today. So this is what those web pages look like. So a web page for each material kind of looks like that. That's the web page on polyethylene pipe for geothermal. This is just the top of it, web page on CPVC, on PEX, on PERT, and on polypropylene. And if I was live online, I could scroll down the web pages and show you more the kind of information you'd find there. So on the polypropylene page, you'll find links to all the standards that we talked about today. So if you want to get right to the ASTM standard for polypropylene, that's a live link that'll get you right there. If you want to read some other documents about polypropylene, here's some live links to different documents from PPI and others about polypropylene materials in this case. And if you want to find out where do I buy polypropylene, here's links to the member companies of our organization that actually make polypropylene piping systems are listed right there. So you can find a lot of good information on our website. We have a web page for every application that we talked about today. This is the one all about hydronic heating. Here's all the different application web pages we've got. We've got lots of different technical publications intended to answer questions that come from the field. So just go to a webpage, and here's a few different technical publications that you can get and download for free. If you don't find something that you're looking for in our website, let me know. Maybe we have to develop it. The intent is to have a publication to address all the questions that come up. And then for presentations that we do like this one, all of our slides also go on our website. So sometime next week, these slides from today will also be on a webpage for our presentations. And we are an ASPE CEU provider. So if anybody wants me to talk at an ASPE chapter meeting, I'd be happy to do so with this or another presentation. So that's it. It's 3:30. This is the end. We hope you enjoyed the presentation. Really cool mechanical room image right there. But with that, these are all the things we set out to do, and I think we did it. So I'm happy to stay for questions, but Jean-Claude, a question, please.
So you talked about the PECs before and the cold expansion. Now, there's different types of PECs. Does that apply to all types of PECs?
According to the standards, yes, it does. But each manufacturer has to endorse it on their own. So what I didn't get into in the details is, for all these different fitting systems, to know if a given piece of PEX is compatible with a given fitting system, you have to check the markings on the PEX to make sure that that piece of PEX has been tested and certified with that fitting system. So for the cold expansion fitting system, you would look at a piece of PEX, and if it says F1960 on the tubing, then it's compatible. If it doesn't say F1960, then it's not compatible with that piece of PEX. Thank you for asking.